Hi, thank you all for coming. So today I'll talk about our paper on distributed key generation with properties high threshold and also in asynchrony. So what this talk is really about is if you have these problems which are distributed key generation or other related problems, I want you to look at those problems in a slightly different way so that you can design more efficient and with much better properties. So this is a joint work with Zhuolun from Aptos, Lefteris from Austria, and my advisor Ling. So let's get started. So this is the outline of my talk. And I'll start with definitions. So before I describe what distributed key generation is, let's just look at this very classic primitive called threshold secret sharing, which is parameterized by these two things, n and l plus 1. So this is a mechanism to share a secret into n shares. Let's say Alice has a secret z, and then she wants to share the secret into multiple pieces. So the property that we want is that any subset of l plus 1 or more shares should be able to recover the secret. But if you have any subset of L or less shares, you learn nothing about the secret. So this is the classic property of threshold secret sharing. So this is one example of Shamir secret sharing. So what you do, you embed the secret as a constant term of a low degree polynomial. Like here, I want 5,4 threshold secret sharing, so I will embed the secret as the constant term of a degree 3 polynomial. And each share will be one evaluation point on this polynomial. And since this is a degree 3 polynomial, any 4 points on this polynomial is sufficient to recover the polynomial and hence the secret itself. But you can also argue that if you are given 3 or less shares, you learn nothing about the secret. So I think most of you are familiar with this very basic concept. So but here we are working with a setting where one party has the entire secret. But in decentralized setting, we don't always have a party that knows the entire secret. And sometimes we even don't want such a party to exist. For example, in consensus, this is a protocol among mutually untrusted parties, so we don't want anybody to have the secret. Similarly, in threshold wallets, we don't want anybody to have the secret. Other examples include Oracle service. So a distributed key generation, or DKG in short, exactly solves this problem. So how do you generate the shares of a random secret key in the presence of with mutual distrust? So intuitively, what it is, so this is an MPC protocol among a set of parties, such that at the end of the protocol, party 1 will output Z1 and some common knowledge, PK and threshold public keys. Party 2 will also output Z2, so on and so forth. So these ZIs are the Shamir shares of this secret Z. And we want that the secret is hidden from the adversary. And the public keys or threshold public keys are deterministically defined from these. Okay? So in this talk, I want to focus on asynchronous networks. We want to design DKG protocols for asynchrony, where the message delays between honest parties can be arbitrarily long. That's the property we have in the network. Okay, so DKGs have many applications. For example, you can use DKG to build threshold signatures as a building block for threshold signatures, which will have other applications in consensus. You can also use to build threshold encryptions, randomness beacon, and many other things. Okay. So since this is an MPC protocol, if you have ever looked at any MPC protocol, we first design an ideal functionality that we want to implement. So let's just look at the ideal functionality. So this ideal functionality has some parameters like elliptic curve groups and so on and so forth. So and there are 3 inputs. So the inputs are the number of faulty parties and the number of total number of parties and a polynomial degree from the Shamir secret sharing scheme. So what this ideal functionality does, it samples a random polynomial g of x of degree L, and then it defines the secret to be the constant term of the polynomial. So I'm repeating what I said earlier. And then the share of party I is the polynomial evaluated at I. And it computes some common information, and then this ideal functionality will send the corresponding share to the corresponding party. So Zi along with the public information to the ith party. So this is the ideal functionality that we are interested in implementing, and we call it a high threshold DKG when the polynomial degree is higher than the number of faulty nodes in the network. So that's the definition. Okay? And why high threshold DKGs are useful? So you can use it to get better efficiency results in consensus. You can also use it to get better higher fault tolerance because the degree is larger, so you need more shares to use the secret. You can also get better privacy in threshold encryption, and there are many other applications. Okay, so this is the background. Now let's look at the DKG template. So if you ever looked at any DKG protocol since past 20, 30 years, this is the template you'll see. So how these protocols work, so a building block for these protocols is something called this verifiable secret sharing. So this is a secret sharing in the presence of malicious parties. So even the dealer can be malicious. Okay? Let's say we have this building block. So how the DKG template works is as follows. So each party will sample a random value and will share it with everybody else using a verifiable secret sharing thing. So everybody will do that in parallel. Then these parties will run a consensus protocol to decide on which subset of parties did their VSS correctly. Okay? Let's say the consensus outputs 1 and 2, which just means that the party 1 and party 2 did their VSS correctly. Then we do the most naive thing, is that the DKG secret will be the sum of the two secrets, like some of the secrets that are output by the consensus algorithm. And then you define the public keys, and the share of each party is the sum of the secret shares of that corresponding secrets. So what's the intuition here? Intuition here is the consensus will output more than T indices, which means the consensus will include at least one honest party. Hence, the main secret key will remain hidden from the adversary. So this is the intuition of existing DKG protocols. Okay, so given this framework, and this is the framework you'll see in all the papers, so if we want to design a high threshold DKG, where we want the secret to be shared using a larger degree polynomial, what do? We take this template, and we replace this VSS using high threshold VSS. This is the most natural construction, where each parties will share their secret using a higher degree polynomial. That's what we tried in one of our previous papers. But the efficiencies are not good. So if you look at the numbers here, with low threshold, we get very good efficiency. But when we go to high threshold, where the degree is 2t, the efficiency, like runtime, becomes like 15, 16 times more. Similarly, the bandwidth increases by 5 to 6x. So why are these high threshold synchronous DKGs are so expensive? The underlying cause is that high threshold verifiable secret sharings are more expensive to design in a asynchronous network. So I won't go into the details of why that is the case, but you can trust me on that. Okay, so what is our approach? And this is the one single crucial slide I want you to take home, is that we want to think about this distributed key generation problem as a new problem. So this is, we say this is a problem nothing but sampling a secret random polynomial. But if you look at the literature, you just feel that DKGs has to do VSS and add the polynomials. But that's not how I want you to think about. You should think about this as sampling a random polynomial such that each party gets 1 point on the polynomial. So now if you think about DKGs if this way, things become much more easier. Now let's look at the ideal functionality one more time. So what the ideal functionality is doing is also doing the same thing. It's sampling a random polynomial, and it's giving 1 point to each party. Okay? And we call it high threshold whenever the degree is higher than t, but we'll design a protocol that also can achieve the same degree t, so I'll just call it more than or equal to t. Okay? So now we are in a different problem space. Now we want to, this is what we call distributed polynomial sampling. So we want to sample a secret random polynomial. And how do you sample a secret random polynomial? You sample random coefficients. So if you want degree L polynomial, you just have to sample L plus 1 random coefficients. Okay? So let's try some approaches. So here's what we know how to do DKG. So we can use the same framework to sample one of the coefficients, because we know this coefficient has contributions from honest parties. So this coefficient Z0 will be random. So we know how to sample one random coefficients. So we can do this L plus 1 of them in parallel. Okay, this will work, but of course this is not efficient. You can do much better by using a randomness extractor. So I won't go into the details of what these things are, but this is how our protocol works as follows. So we know only one thing to do. We just do all n parallel VSS, and then we'll run the consensus algorithm. Then we can program the consensus to output n minus t VSS indices. Okay, this is possible. Then we take this VSS, all the values that the consensus output, and put it as a vector or as input, and then we multiply it using a matrix. So what we are doing is, here we have contributions from honest parties, and we are extracting all the entropy into some t plus 1 random values. That's what we are doing. So that's why we call randomness extractor. So why t plus 1? It's because t plus 1 is n minus 2t. So if you look at the input source of the randomness extractor, there are n minus t non-zero values, but t of the values could be from malicious nodes. So the amount of entropy this input has is n minus 2t. So that's the maximum we can extract. Okay, so now we know just by doing a single VSS how to extract t plus 1 random coefficients. But we want L plus 1 of those. How do you do it? Well, you do the most naive thing. You just ask each party to share 2 secrets instead of 1. And then you generate first t plus 1 secrets using the first set of secrets. And you generate the remaining coefficients using the second set of secrets. Okay? Nothing fancy happening here. And one thing you want to know that the performance of doing this is as very same as the low threshold DKG. So we are doing only 2 secrets instead of 1. And another crucial point here is the degree of the polynomial now can be arbitrary. It is no longer tied to the total number of parties that are running the protocol. That's another crucial property that we are getting. Okay? So now, okay. So given now we know how to sample L plus 1 random coefficients, we can define this natural polynomial z of x using these as coefficients. And each party at the end of what I described so far will have a secret share of these coefficients. That's what we have achieved so far. But what we instead want, if you recall the DKG functionality, we want that each party gets 1 evaluation point on the polynomial. So we still have some tasks to do, but you can do that using 1 extra round of communication. Okay, so how does it work? So let's define this secret shared polynomial. Each party can take the secret shares of the coefficient and then define a local polynomial. And these parties will evaluate the secret shared polynomial at 1 all the way up to n. Then parties will get secret shares of evaluation point. So now you note all these operations that I did are local operations. Okay? But we're a little bit close, but not that close. We want that party 1 have z evaluated at 1 using the plain text of it, but not the secret shares. So what do we do instead? Each party will, party 1 will send z of 1 to party 1, share of z of 1 to party 1, share of z of 2 to party 2, and everybody will do that. As a result, party 1 will collect secret shares of z evaluated at 1 from t plus 1 or more nodes. And once it does that, it can locally reconstruct the final secret share of it, the final secret share that it wants. Okay? So this is the total protocol. This is very simple, and the key point is to think about this problem in a new way. Okay, let's quickly look at the evaluation results. So we implement, and we get the performance overrate is about 30% because we have to do some extra computation on an extra communication cost. Similarly, the bandwidth overrate is also about 30%. Okay? So let's just look at one slide on extension. So the one property that I showed that from secret shares of coefficients to the evaluation points, there is only 1 round of interaction. 1 round of interaction from the left to the right. So we call it non-interactive. So since this is a non-interactive property, what you can do, you can swap out. You can have a new set of nodes on the right. You can ask the old set of nodes to do the entire protocol, and then you can just do a handoff. We call it non-interactive handoff. And since the degree of the polynomial is no longer tied to the number of parties, you can increase the number of parties on the right. So we use this to get much nicer other properties like proactive secret sharing, distributed key generation as a service, and secure multi-party computation in general. So in summary, we present a protocol on high threshold asynchronous DKG. It has these asymptotic numbers. The efficiency of the protocol is same as the low threshold DKG. And we prove its security in the real and ideal paradigm. And we also show distributed polynomial sampling and its applications. Here you'll find the code, and thank you.